Now can you see here I have a light, and you notice that it is just ever so slightly on. Now what do you think is going to happen if I increase the current? Now clearly what you'll notice that it increases in brightness, but did you notice something else? It also changes in colour. It went from a yellowish, orangey colour to a more whiter colour. But do you know what else also changes? Here's a clue. I'm going to have a look at what the thermometer does in terms of reading the temperature of the filament. So the temperature also increases. So we somehow have this relationship with the temperature and obviously the colour as well. That is, as it gets brighter and it changes from orange to white, the temperature seems to be increasing. So now we seem to have obviously a relationship between the intensity and temperature, but also colour and temperature. Now, wouldn't it be good if we were to measure the colour of stars and by that work out what temperature it is? Clearly there's some sort of relationship. Because astronomers want to know about the temperature of stars, because if you know about the temperature of stars, you also know about the inner workings of the star. How do astronomers actually measure a star's surface temperature? Well, stay watching. Today we're going to be looking at the physics of colour and how they actually do measure the temperature of stars by examining the light that comes off stars. So let's have a look at something you're probably familiar with. Let's say I'm making my coffee and I put my pot onto my stove and I turn it on. Now it starts to get warm, which means it's releasing infrared radiation. But now it's starting to glow. It's releasing visible light. Now if my stove was able to do it, if I were able to increase the temperature even more and more and more, I would get yellow, white, and possibly even blue. So now what we have is some sort of relationship between the temperature of an object and the colour of the object as it's releasing energy. But what's exactly going on here? And in fact, a number of scientists in the 19th century were very interested in the intensity of the object radiating energy, that is, the amount of energy that was given off per square metre of that object with relation to its temperature. But the first problem is, how do you get an object to be releasing energy that is just due to its heating up? That is, there's no reflection involved. Now, in order to understand a little bit about the light that is giving off an object that is getting hotter and hotter and hotter, we need to be mindful of something. So take, for example, this piece of copper. This copper is absorbing some radiation around it, but generally speaking, it's reflecting also a fair amount of orange light. So if I now start to heat this piece of copper up, just like my stove, it will be releasing obviously infrared radiation, and then into the visible spectrum it will start to glow. But if I then want to analyze that light coming off it, how much of it is because it's hot and how much of it is because, well, it's already orange and reflecting orange light? And so this object is not really good to study a relationship between the light or energy coming off it and obviously the temperature of this particular piece of metal. So obviously we want something that absorbs and reflects little. And so now I have this graphite block. Now it's black or almost black. And in this case, if it starts to heat up and it starts to change color, well, its color is due to the fact that it's heating up. That's a better model in terms of deciding whether there's a link between the light or the energy coming off it and the temperature of the object in question. But this is still not ideal. Why? Well, you can see it, which means still light is being reflected off it. You want something that absorbs all the energy coming onto it. In other words, it doesn't reflect any light. And if it doesn't reflect any light, well, then it's truly a black body. It is completely black. Now this introduces the concept of an ideal black body. That is, it's an object that absorbs all the radiation falling onto it. As a result, it then re-emits it in the form of electromagnetic radiation. Well, you probably already know what I mean. You wear a black t-shirt on a bright, sunny, hot day, well, it's going to absorb all the light energy, and as a result, it heats up. In other words, it's emitting infrared radiation. But how do you go about making that? So a number of scientists started to investigate the concept of black bodies by using boxes with cavities. That is, if you have a small hole inside a box, then you're not going to see any light coming out of that box due to reflection. That means if you then start heating up that box, if there's any glowing out of that hole, it will be due to totally the internal temperature rising within it, and therefore no reflection. So what resulted was a set of data that produced a graph that looks like this. And this is now called the black body curve. And you'll notice that it has a peak, but it drops off significantly on either side from shorter wavelengths to longer wavelengths. Now, two relationships came out of the latter part of the 19th century that we need to take note of. The first was by Joseph Stefan, who noticed that there was a relationship between the temperature and the power output by way of a fourth power. Now, Ludwig Boltzmann was able to derive this theoretically, and now what they developed was now known as the Stefan-Boltzmann law. Now, that means if I double the temperature of my object, the power output or the energy output is basically 2 to the power of 4 times brighter, and so as a result, 16 times brighter. The second important relationship we need to look at was developed by Willem Wien. Now, what he noticed that there was a relationship between the temperature and the wavelength where the peak of the black body curved. And what he noticed first was that as the temperature increased, the peak increased as well. Now that ties in with Stefan-Boltzmann's law. But he also noticed that as the temperature increased, the peak shifts to shorter and shorter wavelengths. In other words, there was an inverse relationship between the temperature and the wavelength that was the peak of the black body curve. And this has subsequently become the Wien's displacement law, which says that the maximum wavelength is equal to a constant divided by the temperature. In other words, it's an inverse relationship. So you could now, in essence, use that to determine the temperature by looking at the color, because that's where the peak is in terms of Wien's law. Now, you can't, and there's a problem with this line of reasoning, and there are two problems here. And the first, we need to look at the black body curve itself for the sun. Now, if we examine the black body curve and then compare that to the black body curve of the sun, you'll note that there is actually a difference, particularly if we are examining the sun from the Earth, where we're seeing light pass through the atmosphere. And the point is that yes, the black body curve of the sun approximates a true black body curve, but it's clearly different, and there's a reason for this. And the reason is that the light that the sun emits is going through two atmospheres. First, the atmosphere of the sun itself, and then if we're doing ground-based telescopy, but then we're also looking at the light as it passes through the Earth's atmosphere. And what the Earth's atmosphere and the sun atmosphere do is that they absorb certain wavelengths. And so as a result, both the intensity and also the color changes as a result. Now, if you look at the black body curve for the sun, you'll notice that the peak wavelength sits roughly in the yellow-green section. In fact, it's around 520 nanometers. And so that's sort of a greenish color. And so you could argue, is this the reason why the sun is green? Well, again, there's a problem here, and that is because the way we perceive the light as it strikes our eyes. For starters, let's have a look at the range of visible wavelengths that the sun is actually emitting and therefore striking our eyes. If we were to see there, you can see that they don't arrive with all exactly the same intensities or radiances. And as a result, you could argue that there is more of green and less of red and less of blue. But our eyes are just not that sensitive enough to pick that variation. And so for all intents and purposes, when we see all those colors, all the parts of the visible spectrum hit our eyes, we will see them at the same intensity. And so for all intents and purposes, we see white light. So the sun is white. Now, there's also another problem that we have to consider when we look at light in terms of how it interacts with our eyes. And we need to understand how our eyes work. Our retina contains two types of cells. The first are the rods, which detect brightness, and the second ones that are detecting color, which we refer to as the cones. Now, we are what we refer to as trichromatic. That is, we detect three colors. So we have three types of cones, and one is dealing with the long wavelengths, one in the mid wavelengths, and one in the short wavelengths. They are often labeled as red, green, and blue, but we need to be careful again with that. So if we look at this particular graph, you see the response curves for the three types of cones that we have. And you'll notice that a couple of things is that they don't respond to just red, green, or blue specifically. They respond to a range of wavelengths. And in fact, there's a lot of overlap as well. And secondly, for example, if you look at the response curve for the long wavelengths, you'll notice that it actually peaks roughly in the yellowish area. What happens therefore when light hits our eyes? Well, if we just were to see just red light, like now, then your long wavelength cones are responding and your brain interprets this as red. And that's similarly if we were to fire green light or blue light. But what about, let's say, something that's yellow? Well, if you see yellow, your long wavelength cones are being triggered, but so are your mid wavelength cones being triggered. And as a result, your brain interprets that as yellow. But you'll notice that even in terms of the yellow, that the two particular types of cones, the long and the mid, don't actually are responding at exactly the same intensities. And what about color hues? That is, where we see all very different shades of color. So for example, let's talk about pink. It's a hue. Well, how does that work? Well, in essence, you get to see hues when there is a marked difference between the wavelengths that you are receiving. So let's say we were to fire off your long wavelengths, your red wavelengths, and we were to throw in some blue light, and so now your short wavelengths are being fired. And as a result, because there's a marked difference between the two, in this case, you're going to see that hue of pink. So when you see all the different wavelengths of the colors of the rainbow, you are not responding to those individual wavelengths. You're responding to your long, mid, and short wavelength cones firing, and your brain is interpreting the colors that you see. And that, of course, has implications on how we see the color of stars. Now, in 2021, so earlier this year, Jan-Vincent Harre and René Heller published a paper called The Digital Color Codes of Stars. Now, in this paper, they simulated a variety of main sequence type stars and modeled the color that we would see first by ordinary blackbody radiation, and secondly by a computer model called Phoenix and T-Lusty, where they took into account the range of sensitivities of our own eyes. In other words, 360 nanometers to 830 nanometers, and then show what the color that we would receive. And they got some really interesting results. So here are the color representations that they found, and in the top row you can see the simulation based on the black body curve, and the bottom via the Phoenix situation. And here we've got three different temperatures shown, and the first is 2700 Kelvin, then 5200 Kelvin, and then 8000 Kelvin. And you'll notice here there is a difference in the color that we perceive. So the point is this: you can't use the color of a star to determine the temperature of that star. So at best, a radiating body is hot because it glows red. It's hotter because it glows yellow or orange and so forth. Or really hot if it starts to glow white and blue hot. But that is as far as it goes. So now, what do astronomers do to measure the temperature of the star? Well, first, they don't use Wien's law. But what do they do? Well, there is actually two methodologies that we're going to be looking at. The first methodology they use is they use filters. Now, what do filters do? Well, filters allow the transmission of certain wavelengths to pass through and block others. So a red filter will allow red light to pass through, but other wavelengths such as blue won't, and so therefore will appear black. And similarly with the blue filter. Now, in the terms of astronomers, is they examine stars using two types of filters. Now, they don't use this red filter and this blue filter. Their filters are a little bit different, but in essence, they're labeled as blue and visual. So the blue is basically transparent to your shorter wavelengths, anywhere from 400 to 480 nanometers. Whereas your visual filter is basically transparent more to the 500 and 600 nanometer range, and it's called visual because it's roughly the sensitivity of our eyes. Now, to examine this, let me show you this image here. So what we're going to do now is to see what a visual filter and what a blue filter does, is we're going to simulate this by using Photoshop. Now, this is an image of Teson 5. Teson 5 is a globular cluster which is sitting in the bulge of the Milky Way. And you can see a whole range of different colors here, from the oranges to the blues. And we already know that the oranges are a little bit cooler and the blue ones are a little bit hotter. Now, I'm going to highlight these two areas so we can see what's going on. And I'm going to first look at what a red filter or a visual filter will do, what's going to happen to the blue stars and what's going to happen to the red stars? Well, you'll notice that the blue stars become dimmer, so their magnitude actually becomes a bigger number. And the red stars, of course, are staying relatively bright because the red filter allows the reddish light to pass through. So what if I now do a blue filter? But I want you to take a notice what happens to the red stars in particular. You notice they become significantly dimmer. So now what we have is that there is a difference in brightness of a particular star if we examine it by terms of a visual filter or a blue filter. Now, in my previous video on stellar magnitude, I discussed how a star's magnitude is determined by its distance and obviously its intrinsic brightness. And we had this idea of a magnitude scale. And so what we do here is we determine a star's magnitude by way of a blue filter and a star's magnitude by way of a visual filter. And now because we have different magnitudes, we can subtract the two. So for example, if we were to use a blue filter and look at a blue star, it would still be very bright. So the magnitude would actually be a very small number. Whereas if I were to do it with a visual filter, that star's brightness would diminish significantly, and so therefore its magnitude is bigger. And so if I subtract the two, I actually get a negative number. And similarly, if I did this for the red star, if I subtract the differences in magnitude, in that case, I would get a positive number. And so what we now have is a value called the color index, which is simply the magnitude differences between blue minus visual, and that allows us to establish a relationship between temperature. Now, it's more complicated than that. So astronomers then work out the color index of a star, and using computer models, they model the color index with the associated temperature for that particular star. So there's your first method, the color index method. The second one we want to look at is by looking at what we refer to as spectral classes. Now, in the late 19th century, when they examined the star's spectra, they noticed that there were certain lines missing. Now, these lines are absorption lines and are predominantly based on hydrogen, but also other elements as well. And initially, when they categorized that, they noticed that there was a relationship between these classes. That is, there were some that had certain amounts of spectra missing and others. And so as a result, what became known as the Draper system is basically a series of classes. They labeled them A, B, C, D, E. Then in 1901, Annie Jumpkinnon, who should actually receive more credit for the work that she's done in history, revised the system. She concentrated specifically on the hydrogen lines, which are referred to as the Balmer lines, and she rearranged the letters and also dropped a few letters as well. And so therefore her new system, which is now referred to as the Harvard system, and it's the system we now use for spectral classes, starts with O, B, A, F, G, K, M, and L. O is your hottest, and your L and your M are your coolest stars. Now, the thing is that also within each of those classes, we can divide them into subclasses. And so a number of decades later, they developed subclasses in between from 0 to 9. And so you have O0 as you being really the hottest of the one, and O9 a little bit cooler. Now, our sun is a G2 type star. So it's a G star, but it's a G2 star, and that is linked with the temperature of the star. Those two systems combined allow astronomers to work out the temperatures of a star. And of course, using the temperature, you can know more about the inner processes, about the mass, and about the lifespan of that star. So back to the paper by Harre and Harre. Here we have a selection of main sequence type stars, and you'll notice the temperatures and the spectral classes down the bottom. And again, this is based on their computer modeling, based on their Phoenix model. Now, the point we drive home here again is that the color we see are generally shades of orange to shades of blue, with white somewhere in between. What we don't see here are red stars. In fact, red dwarfs appear as sort of a darkish orange. We don't see purple stars. O2 is a very hot star, but it is still blue. And clearly, we don't see yellow or green either in between. So why do people think the sun is a yellow star when in actual fact it's white? Well, I think our atmosphere has a part to play here, and it's because our atmosphere scatters blue light. Now this is called Rayleigh scattering. I have a video which examines that specifically, and I'll put the link up below. But in essence, as the sunlight enters our atmosphere, some of the blue light is scattered away, leaving obviously what's left over reaching our eyes. Now when the sun is directly overhead, our atmosphere is quite thin, relatively speaking. So therefore, you're going to get very minimal scattering of the light that's receiving towards us, and as a result, you're going to see white light. And so that's why the clouds are white, because they're reflecting that white light. But as the sun sets closer and closer to the horizon, of course, it's the same at sunrise, then it's passing through a lot more atmosphere. And because of the fact that there's a lot more scattering going on, what we get left over now appears yellowish. And so as a result, we see those colors on our clouds at late in the afternoon or early in the morning. They appear a little bit more yellows, even orange or red, depending on how low the sun is. Needless to say, an astronaut in orbit does not see a yellow sun. They see a white sun. Well, I hope that has helped you understand a little bit about the nature of color and light and temperature, and how astronomers determine the temperature of a star. Please like, share and subscribe, and put a comment down below if it's been helpful for you. Check out my videos on Rayleigh scattering, on the HR diagram, and also stellar magnitude as well. Maybe consider watching some of my podcasts where I've interviewed a number of scientists. Many of them have been astronomers and astrophysicists. And please consider supporting me via Patreon to help me produce more work. My name is Paul from PhysicsHigh. Take care, and bye for now.